Forces shape our entire universe. Gravity is the most famous force of all. It pulls everything towards everything else proportional to their mass. Gravity explains why apples fall from trees, why we do not float off into space, and why the moon stays in orbit around Earth. Earth itself orbits the sun. Einstein taught us that gravity is the curvature of spacetime caused by mass and energy. Massive objects, like planets or stars, essentially create a dip in the fabric of spacetime, and smaller objects roll into that dip. This elegant explanation unifies the falling apple with the orbiting planets, showing how a single force governs motion on both cosmic and everyday scales. Gravity ultimately holds galaxies together. The electromagnetic force is everywhere you look. It is the force between electrically charged particles, combining both electricity and magnetism. This force holds atoms together, preventing electrons from flying away from the nucleus and forming stable molecules. Every time you touch something, see light, or use an electronic device, you experience the electromagnetic force at work. Magnets sticking to your fridge, static electricity making your hair stand up, or the glow from your screen are all direct manifestations of this force. The electromagnetic force underlies all of chemistry and biology, dictating how atoms interact and form the complex structures of life. It also powers all modern technology, from simple household appliances to advanced computing systems, making it arguably the most impactful force in our daily lives. In the microscopic world, we find the strong nuclear force. This force is dramatically stronger than gravity or electromagnetism, but it has an incredibly short reach. Its main job is to glue together the protons and neutrons within an atom's nucleus. Protons, being positively charged, naturally repel each other through the electromagnetic force. Without the strong nuclear force, atomic nuclei simply could not exist, and neither would any elements heavier than hydrogen. This immense binding energy releases in nuclear reactions, showcasing its raw strength. This power manifests in the destructive force of atomic bombs and in the controlled generation of energy within nuclear power plants. It truly defines the structure of matter and the energy potential within it. The weak nuclear force is our fourth and final fundamental force, often the least understood. Unlike its strong sibling, the weak force causes certain types of radioactive decay, a process where unstable atomic nuclei transform. It primarily allows quarks, the even smaller particles inside protons and neutrons, to change their flavor, effectively turning a neutron into a proton or vice versa. This transformation enables nuclear fusion in stars, like our sun, where hydrogen converts to helium. So, while scientists call it weak and it has a very short range, it indirectly creates the energy that makes life on Earth possible, acting as a cosmic particle changer. Friction is a force we experience every moment. It is a contact force that always opposes motion or the attempt of motion between two surfaces sliding or trying to slide past each other. Without friction, walking would be impossible, cars could not drive, and nothing would stay put on a tilted surface. Consider its importance for car brakes to work or for gripping objects with your hands. However, friction also creates wear and tear, generates heat, and requires more energy to overcome. Engineers try to minimize it in moving parts with lubricants. It is a double-edged sword, necessary for our daily lives, but also something we constantly work to manage. The normal force relates to contact. Whenever an object rests on a surface, that surface pushes back on the object perpendicular to its own plane. This is the normal force, and it prevents you from falling straight through the floor. If you place a book on a table, the table exerts an upward normal force on the book, precisely balancing gravity's downward pull. This force is dynamic. If you push down harder on the book, the table pushes back harder. It is a reaction force, always adjusting to prevent objects from interpenetrating surfaces. Without this force, the solid structures we take for granted simply would not hold up, demonstrating its fundamental role in providing structural integrity to everything around us. Imagine pulling on a rope. You are dealing with tension. This pulling force transmits through a flexible connector like a rope, string, cable, or chain when it stretches taut. When you hoist a bucket of water from a well, the rope experiences tension. In a suspension bridge, the massive cables are under immense tension, supporting the entire roadway. Tension acts along the length of the medium, effectively pulling equally on the objects at each end. It proves essential in countless engineering applications, from elevators lifting heavy loads to clotheslines holding your laundry, allowing forces to transmit over distances and around corners. As objects move through the air, they encounter air resistance, also known as drag. This is a special type of friction exerted by air particles against a moving object, always acting in the opposite direction of motion. Consider a skydiver falling. Air resistance pushes upwards, slowing their descent until they reach terminal velocity. The shape of an object dramatically affects how much air resistance it experiences. Streamlined cars and airplanes are designed to minimize it for efficiency, while parachutes maximize it to safely slow things down. It is a constant invisible force influencing everything from a thrown ball's trajectory to the speed of a high-performance race car, making it a key factor in engineering designs for efficiency and safety. Ever wondered why a massive steel ship floats? Or why you feel lighter in a swimming pool? That is thanks to buoyancy. This upward force exerts by a fluid, whether liquid or gas, that opposes the weight of an immersed object. According to Archimedes' principle, the buoyant force equals the weight of the fluid the object displaces. If an object displaces enough fluid to match its own weight, it floats. If not, it sinks. This force makes everything from naval architecture to the flight of hot air balloons possible, and even helps fish control their depth in water. It literally provides the lift that defies gravity in fluid environments. Sometimes, forces come as a direct push or pull from an external source, and we call this an applied force. This is the intentional effort you exert on an object, acting directly upon it. When you kick a soccer ball, push a door open, or lift a heavy box, you apply a force. It is the most intuitive type of force because it originates from a direct agent, whether a person, a machine, or even another object impacting something. Applied forces initiate motion, change direction, or deform objects, causing them to accelerate according to Newton's second law. They help us understand how objects respond to external interaction in physics, literally driving all the deliberate movements we make and observe in the world around us, from a child pushing a toy car to an engineer designing a robotic arm. Consider a slinky, a car's suspension, or the mechanism in a retractable pen. They all use spring force. This restoring force exerts by an elastic object, like a spring, when it compresses, stretches, or twists. The spring force always acts to return the spring to its original, equilibrium shape. The further you deform the spring, the greater the force it exerts, a relationship known as Hooke's law. This principle finds use in countless devices, absorbing shocks in vehicles, measuring weight in scales, and storing potential energy for later release. It is a remarkable example of how elasticity gives rise to powerful and predictable forces. Centripetal force is not a fundamental force itself, but rather a net force that acts on an object to keep it moving in a circular path. Without it, the object would simply fly off in a straight line, tangent to its circular path due to inertia. For example, when a car rounds a corner, friction between the tires and the road provides the centripetal force. For a satellite orbiting Earth, gravity acts as the centripetal force, continuously pulling it inwards. In a swing ride at an amusement park, the tension in the chains provides this inward pull. It directs all circular motion, constantly pulling objects toward the center of their rotation. From the tiniest atom to the vastest galaxy, forces are the unseen architects of our universe, constantly pushing, pulling, and shaping everything around us. Understanding them unlocks the secrets of reality itself. Which of these forces do you find most fascinating, and why?